Thank you. It's great to be here. I will give you a brief overview of clay-hosted rare earth deposits in Australia and discuss some existing challenges and exploration considerations. As many of you know, rare earth elements are in high demand, which is expected to increase by 7 times by 2040. Clay-hosted or ionic adsorption clay deposits are a valuable source of rare earths. Their input in the total resource is less than 4%, but they account for over 80% of the world heavy rare earth supplies. These deposits, formed by weathering, have many characteristics very attractive for mining. Elevated content of magnet and heavy rare earths, high tonnage mineralization, though lower grades, low operating costs due to near-surface mining, low stripping ratio, no blasting required, quick and cheap to define resources by shallow air core drilling, no crushing involved, simple recovery techniques using cheap chemicals at room temperature, and also importantly, there is low radioactivity. The majority of clay-hosted deposits are located in Southeastern Asia. Over 200 mines are in the southern China and 100 in Myanmar, adjacent to the China border. Only a few deposits are known around Africa and America, though 2 of them in Brazil are of a large scale. A number of deposits were recently discovered around Australia. Let's have a look at them in more detail. In Australia, most of occurrences spread around western and southern parts of the country, clustering in the Esperance region and in the Yilgarn and Golek cratons. Most of the deposits are hosted by granitoids and felsic volcanics, with Cappamara in South Australia and deep leads in Tasmania, developing over sedimentary rocks. Australian deposits, red circles here, are moderate and small in size. They are generally comparable in size with the Chinese mines, though grades are generally lower. 2 large Brazilian deposits contain over 1 million tons of rare earths each, with Caldeira, discovered last year, being highest in grades. Blanket-style mineralization in residual regolith developing over granites is the most common type deposits around Australia. The Esperance region is the largest exploration hub at the moment, with an actively exploring area 250 kilometers long and 60 kilometers wide. The Newman deposit, now Salazar project, found in 2011, was the first in Australia. All the other prospects have been discovered for the last 2 years. Mineralization, they developed in weathering crusts over Proterozoic granites and gneisses. It's hosted by saprolite, clay zone and subrock, forming continuous subhorizontal blankets up to 20 meters thick. Rare earths are mostly recoverable by strong acid leaching, indicating that metals occur in a colloidal form. Percentage of easily leachable rare earths is commonly low, less than 10%. Exploration for clay-hosted deposits in Australia is currently driven by grades. Most of discoveries were made accidentally, exploring for other commodities. This mineralization type, previously known as only found in China, is relatively new to Australian industry. Existing exploration models and knowledge base are still at the development stage. There is a steep learning curve for geologists starting new projects here. A lot of unknowns, lots to learn about the mineralization formation, critical controls, and the best exploration approaches to take. Although a mineral system looks relatively simple, there are lots of issues to consider in the targeting process. The system is generally the interplay between geological settings and magmatic evolution on one side, and weathering processes on another side. A two-pronged targeting approach is required, chasing both fertile source bedrock and kaolinite-rich residual regolith. And talking about grades, average crustal abundance of total rare earth oxides is around 200 ppm, and only moderate five-fold enrichment is required to upgrade background values to the economic 1000 ppm level. This is much less gradient compared to many other metals. For example, 300 times enrichment is required to upgrade gold background abundances to 1 ppm level. So this means that rare earths are not that rare. So why we have not too many deposits around Australia? Apart from weathering-related issues, grades are greatly affected by recovery problems. Only easily leachable part of mineralization should be considered, because traditional cheap processing by ionic solutions only extracts this part. Most of the Chinese deposits and Caldera in Brazil and Tantalus in Madagascar show recoveries above 60% benchmark. In comparison, most of Australian deposits and prospects are low in the easily leachable component, except the deep leads in Tasmania with 40% recovery. Presence of adsorbed rare earths is the best case scenario, as requires low acid consumption and subsequently is relatively cheap. Dealing with stronger bound forms of rare earths, colloidal, mostly locked in iron oxides, or refractory minerals requires more aggressive leach conditions and more expensive. With stronger acids, which is reflected by decreasing pH on this graph, cost of chemicals alone can get higher than product revenue. The recovery of metals is often a decisive factor for further project development. Standard leaching recovery tests are relatively simple. Their completion is strongly recommended at very early stages of exploration to ensure viability of the project. So which host rocks are most prospective for clay-hosted deposits? They are mostly formed over granites, felsic volcanics, and alkaline felsic intermediate rocks. There are no size, geometry, or age constraints reported on the fertile granite intrusions elsewhere. Muscovite and muscovite biotite granites are considered to be the most prospective. Deposits are commonly developed in the marginal parts of intrusions and on the late stages of granite emplacement. Fractional crystallization and magma differentiation are the key processes for concentrating rare earths in alkaline igneous rocks. Late-stage hydrothermal and automated somatic processes are essential for conversion of resistant rare earth minerals into the weatherable species. The second key component of the mineral system is the weathering process, greatly affecting enrichment, partial remobilization, and rare earth fractionation in the weathering profile. Clay regolith, rich in kaolinite and halloysite, is the critical part of the mineral system. Smectites appear to bind rare earths too strongly, preventing their recovery using dilute electrolyte solutions. Same applies to iron oxides. This is thought to be the main reason why mafic rocks, commonly weathered to smectites and iron oxides, are not very prospective for ionic adsorption type mineralization. Subtropical to tropical climates with moderate to high precipitation and temperatures favor chemical weathering to the clay zone formation. And low to moderate denudation rates ensure the preservation of thick regolith profiles. The majority of economic deposits are developed over peraluminous to metaluminous granitic plutons. Most enriched granites belong to high potassium, calc-alkaline to shashanitic series. So highly siliceous, over 70% silica rock compositions, medium to high sodium and potassium, and lower calcium, lower levels of phosphorus, titanium, and iron, which could bind rare earths into immobile secondary phases. And their rare earth signature of the protolith generally controls the rare earth distribution in the subsequent weathered mineralization. Mobilization of rare earths in the weathering zone is mainly controlled by the presence of mineral hosts susceptible to dissolution in acidic groundwaters. Zircon, xenotime, and monazite, most common minerals in hard rock deposits, are resistant to weathering and retain in the regolith. Fluorocarbonites, gadolinite, allanite, and some other species are relatively mobile, releasing rare earths into supergene fluids, and they actually potential minerals to form clay-hosted deposits. Special attention needs to be paid to heavy rare earths. Apart from magnet-type terbium and dysprosium, there are also very highly priced lutetium and holmium in this group. The formation of this type deposits, hydrothermal overprinting on the later stage of granite crystallization is essential, as it commonly upgrades the mineralization by the heavy rare earth-rich fluids. Albite-rich, muscovite, or 2-mica alkaline granites are most prospective for heavy rare earths. Parent granites are highly siliceous, over 75% silica, alkaline, and high in fluorine. They are also depleted in iron, in magnesium, calcium, and phosphorus. The heavy rare earth signature of the bedrock source is commonly not changed by weathering processes and inherited by the clay-hosted mineralization. And to summarize, successful exploration for the clay-hosted rare earth deposits requires a good understanding of both fertile bedrock source and weathering evolution. The presence of easily weatherable rare earth minerals in the source rocks is thought to be the primary control of the desirable ionic adsorption type deposits. And bedrock analysis to be focused on late-stage hydrothermally altered parts of granite and alkaline intrusions, a number of chemical and mineralogical constraints to be applied to identify the most prospective ground. Exploration to be prioritized to the heavy rare earth enriched mineralization type. And regolith studies supported by geophysical data in TORP to be used for identification of continuous blankets of residual clay regolith. So I think Australia has a great potential for discovery of substantial mineral resources of the clay-hosted rare earth mineralization in the near future. Thank you.